everyone, and welcome back to our minute concept. This time, a super in-depth concept, our supercut discussion on derivatives. What I'm going to do for this video is I'm going to bring you guys through almost every topic of derivatives, starting from the limit and the delta definition of derivatives, and then I'm going to bring you all the way through the rules, all the way up until related rates. And basically, what we're going to try to do here is a different type of setup from our different discussions. In physics, what we did was we break down our discussions across around 30 videos, and we have in-depth concepts for each of them. However, for basic calculus, derivatives and integrals, for example, they're very tight-knit topics, and what I'll be doing from here forward is I'll make this supercut video, and I'll take the portions of the different sections of the video about the different topics, and I'll release them as smaller in-depth concepts so that you guys can focus on them specifically. And at the same time, we're also going to be able to have a continuous discussion if your time permits it. So without further ado, thank you for clicking on this video, even though it might be around an hour long. And let's get straight into derivatives. So, what are derivatives? Alright, so in the first part of this Minute Basic Calculus playlist, we talked about limits. And in limits, we were able to discuss that it's the behavior of a graph as it approaches a certain point, right? And limits actually factor in the derivatives in a quite important way. Take into consideration, for example, a graph that looks like this. I'll use the same type of graph that I used last time, another parabola. Okay, now I want to know the rate of change in this parabola, and I also know, for example, I'll draw my x and y axis here. I know that the rate of change is described as slope or rise over run. Now, it's kind of different here because even if I had a grid, my rise over run wouldn't be exact. It's curved. So what I'd use for my formula would be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This is our slope formula. This is average slope. Now, basically what this does is we pick 2 points. Let's say that we're going to use this point here, highlighted by the red, and you want to see the rate of change or the average change from this point all the way here. Now, I don't know what those values are yet, so let's just assign points. Let's say that this one right here, this is, it's close enough to the origin. Let's just say that this is 0, 0. And this one is, let's say around 3, 4. No, 3, 2. There, 3, 2. Using this formula here, y sub 2 minus y sub 1, our average slope would be y sub 2, which is 2, minus 0, over x sub 2 minus x sub 1, which is 3 minus 0. So our slope or our average change would be 2 over 3. But that's just an average. I don't know how much my graph is actually changing at, for example, this point in the middle. I want to know exactly how much it changed. So what can we do? Well, we can get the point of this one here, and we'll do our formula again. So let's say that this is now 2 comma 1, and we'll do it again, and now our slope changes from 2/3 to 1 over 2. And then I want to get even closer. I want to see the rate of change exactly at the origin. So let's get even closer. This becomes, let's say, 1/2 comma 1/2 as well. So that's 1/2 over 1/2, and that's basically just over 1/2. That makes it equal to 1. So our rate of change is now 1. Let me remove this. That's our new rate of change. what are we doing here? Basically, what we're doing is we're getting the slope infinitely closer to the point that we're interested in. And what type of definition does this align with? We're getting infinitely close to something yet we're not exactly there, and we're looking at the behavior of our slope as it reaches that certain point. That right there is the integration of our limits concept in the form of derivatives. Now, the classical interpretation of this, or the more conventional way of interpreting this concept, is through secant lines. Now, basically what we just did was we got the slope of this secant line because we used rise over run. Now, by shrinking it, we're moving this point downward. So instead of it being like that, we're making the secant line a lot steeper. Well, not really steeper, but we're reducing the angle, and we're getting infinitely closer until at one point, let's remove all of these points now here. At one point, the secant line will be so close to this point here that we're interested in that it will look like this. It will look like a completely tangent line. And what is this tangent line? This tangent line will represent the rate of change of this specific point. That is why we need to use limits in order to interpret how to get to that tangent line. And this is where the limit definition of derivatives comes into play. So the limit definition of derivatives can be derived from y sub 2 minus y sub 1 over x sub 2 minus x sub 1 equals m. So let's use this and put it over here. Alright. So we know that we want to have information on the slope at a certain point. So this is our formula that we're going to use. This is what we're going to apply limits on. Now, y sub 2 can be anything now, right? It can be anything now. It will get infinitely close to whatever value we have here. So, how are we going to apply limits? For example, we're going to make this again 0, 0. Okay, and how can we rewrite this in a way that we can apply limits? We can rewrite y sub 2 as just generally f of x. And y sub 1 can now become a new variable, which we will call y0. Same with x sub 2. X sub 2 will become, let's just call it x sub 1, or just simply x minus x sub 0. And this is our m. And our limit statement here, because we're approaching 0, we're going to say that our limit is approaching 0. And that is our slope. Now, let's say that our formula here is f of x is equal to x squared, because this is really just the most basic function here. Now, what can we do about this? What we're going to do now is we're going to substitute our values. But first we have to define what y sub 0 and x sub 0 are. Simply put, y sub 0 and x sub 0 are the coordinates of the points that you actually want to identify the slope of. So for example, we're interested with 0, 0. So 0 in the x is going to be x sub 0. Oops, x sub 0. And the 0 here is going to be y sub 0. So now we'll just replace everything here. F of x is equal to x squared. So we're just going to have x squared here on top minus 0 over x. It's just x because that's our input, minus our desired 0 x coordinate, which is 0 as well. And we're gonna apply limit as x approaches 0. Now, we can simplify this so that we don't get an indeterminate form. We'll get x, the limit as x approaches 0 of x squared over x, which simplifies to x. And identity function. This means that the limit as x approaches 0 of the function x is equal to 0. This is our slope. This is our slope right here. Now, what is the significance of a zero slope? A zero slope shows that there is no change or there is a minimum or a maximum. More on that later. Basically, what we just found is the point where there is no change. It's essentially like your reference point. It shows a maximum or a minimum, and in this case it's a minimum because it's going upward, and that is the origin point. So it's a purely horizontal line because the only line with a zero slope are horizontal lines. Vertical lines do not count because, well, obviously it will become undefined. So now let's try to make this tangent line with a zero slope, and you'll find that we get the same exact drawing as we did earlier, which is, hold on, not purple, let's use red. The tangent line would be like this, perfectly horizontal, even though my drawing is not perfect. There. So that is essentially what it would look like. And this is what we call this formula right here. We're gonna put it over here on this side. This is the limit definition of derivative. Limit definition. Now, what some mathematicians did is they took this version and they optimized it. Well, not really optimized it, but they changed it a bit so that they can represent the change in position using a different variable. And in terms of calculus and a lot of other branches of mathematics and even science, we describe change as delta. Now, what they did was, instead of having f of x be our reference point here, we'll just be using the same exact function, except we're going to be accounting for the delta. And what this allows us to do is, it essentially just makes this a different version of this formula, but we're including the actual change in position, or the change in coordinates. And they found out that the formula could be written like this. It's basically the limit as delta x approaches 0 of the f of x plus delta x minus f of x over delta x. And now this basically is our delta definition of a derivative. Not really much to explain here. This is basically just what they gave us. And the delta definition is also for instances where we don't have the point that we're looking for. And this allows us to get the, what's it called? It allows us to get the equation, for example, of the slope at a given point. And why don't we give that a try here? Okay, so we'll use this formula here. Again, this is the delta definition. Other versions, they use the letter h to represent delta. So for less confusion, we can actually just change our delta value to h, just so that we don't have so many x's in our solution. H here, here, and there. H is just a placeholder, it's just for change, or the delta x. Now let's try to figure out this, let's try to use this definition to figure out the equation of the slope of this function right here, x squared. So what we want to do now is we're going to use GenMath a bit. We're going to evaluate this first, and then we're going to apply the limits after. So the f of x plus h is going to be, let's rewrite it first, the limit as h approaches 0 of f of x plus h. F of x plus h would mean that x turns into x plus h, so we'll have x plus h squared minus f of x, which is x squared. This is over h. Now, to further simplify, we can expand x plus h squared and we can turn it into it becomes x squared plus 2hx plus h squared minus x squared over h. We can see that these two cancel out, and we're going to be left with, hold on, let's use a different pen. We'll be left with the limit as h approaches 0 of 2hx plus h squared over h. We can factor out the h here, so let's just go ahead and do that already. We're gonna factor out the h and we'll get 2x plus h. And we can cancel these two out. So now we're going to be left with the limit as h approaches 0 of 2x plus h. Substituting h into 0 into h rather, we'll be able to get 2x as our answer. And this is also our equation for slope. Now, if we want to find the equation for slope, if we want to find the slope using this equation for the slope rather, we just have to plug in an x value. Now, we were interested with the slope at the origin, so we're just going to plug in 0. And the m at 0 would be 2 times 0, which is in fact 0. And if you also want to examine this using the differentiation rules, perhaps you already know what that is. Using the power rule for on the function x squared would actually get you 2x. So that is the delta definition, as well as the limit definition. So again, these two are basically the most basic form of how to get the derivative of a certain function. The primary difference is the limit definition requires you to have points. You need points here. And that's because of y sub 0 and x sub 0. While on the other hand, delta definition gets you the equation for the slope. The limit definition needs the points, the delta definition needs the equation. And from these, actually, you can make the equations of the tangent line itself. Now, let's try to explore what that means and how we would do that. So, I'm going to remove these drawings here now, since we have them on the other side. Okay, let's try using the delta definition to figure out the slope at this point here. Hold on. Let's use this point right here. Let's say this was, I don't recall what it was. I think it was 3, 2. This point here. And let's use the delta definition. So we want to figure out the slope and the equation of the tangent line. We figured out a while ago that the slope of this is given by, the slope of this function rather, is given by 2x. So our x value here is 3. So we'll plug in 3. 2 times 3. We'll get an answer of 6. Now, what do we do with our slope? To get the equation of the tangent line, all we have to do is use slope-intercept form or point-slope form, depending of course on what you're able to obtain, like the values you're able to obtain. So let's try using slope-intercept form, which is y equals mx plus b. We know that y should be 2. And hold on, let's use a different pen. We know that y should be 2, and we have our slope, which is 6, and we have our variable x, which is supposed to be 3. Hold on. It's supposed to be 3, and we're looking for b plus b. Now, the importance of writing it like this first is so that we can figure out what the missing variable is. Because right now, this entire thing should be equal to 2. However, as we can see, it's not exactly equal to 2 just yet. So, we're just going to do algebra, and we're going to transpose this to the other side, so it becomes 2 minus 18 is equal to b, which is negative 16. So since we have the value of b now, we can rewrite our equation as y is equal to 6x plus minus 16. And this is going to be true because when we plug in 3, we'll get 18 minus 16, which is equal to y equals 2. And that is how you get the equation of the tangent line. You're going to get first the equation of the slope. You're going to use your x-coordinate, the x-coordinate of interest, and then plug it in, and then you're going to use point slope form or slope intercept form. Now, we now know the most basic derivation of the most basic derivation technique, the limit definition and the delta definition. Now, we're going to talk about the rules on their derivation, because this is actually really taxing. This is very time consuming. Now imagine if you had, for example, trigonometric functions where you have waves going like this and you need to get the tangent line here, but their formulas are given, for example, by sine, etc., and you'd end up having to be doing x plus h of every sine function, every element of that function. So that's not exactly ideal. That's why in calculus, differential calculus, we actually have rules that we can follow. For the first rule, the most common and the most used one throughout calculus is the power rule. Okay, so the power rule is described using this formula. So that's basically any number, for example, there's a coefficient here. No. Let's say the derivative of any variable x raised to a certain power is equal to that power multiplied by x to the power of the original power minus 1. In other words, if x is raised to n, then the derivative is equal to n times x to the power of n minus 1. Now let's try that with this function right here. So we have that we need to get the derivative, for example, of x squared. So all we're gonna do is we're gonna multiply this down here, 2 times x, and to the power of 2 minus 1. Now 2 minus 1 is just equal to 1, so we're left with 2x as our final answer. And as you can see, this formula here aligned with what we got with the delta definition, as I said earlier. Now, what's the next rule? The next rule is to understand that the derivative of a constant is always 0. So the constant derivative rule. Constant derivative rule. The derivative of any constant c is equal to 0. So if I want to differentiate, for example, 1, that's 0. If I want to differentiate constants like e, that's 0. Pi, that's 0. That's important for you to know because while they look like variables, e and pi are actually constants. They are numbers that never change. You won't find a textbook suddenly saying that pi is not 3.14 and instead like 300 or something. They're always going to be the same. So that is the constant derivative rule. Now, what is after the constant derivative rule? It's similar to the limit laws. We can actually add our derivatives, and that is the sum of the derivatives rule. And let's use purple for this. So the sum or difference of derivatives, or diff of derivatives. So basically, if we're going to be given a function like this, let's say x to the power of n plus I don't know, let's use different variable, a to the power of n plus b to the power of m minus c to the power of n and lmno, okay, there, and we're asked to get the derivative of this. Basically, all we have to do is apply derivatives to each term, and this is going to equal the derivative, of course, of a to the power of n plus b to the power of m's derivative minus c to the power of o's derivative. And in a polynomial example, we could show that, for example, with the derivative of let's try x cubed plus 4x squared plus 3, and then we're trying to get the derivative of this. Now to get the derivative, we just apply our derivative statement here to all of them. So the derivative of x cubed would be 3x squared, and then we're gonna add that to the derivative of 4x squared, which is 8x, using the power rule. And the derivative of a constant is always 0, so plus 0, or honestly just don't even put it. So this is our derivative. Now this is these first three rules are the most basic because they're going to be the most reused differentiation rules. Now moving on to the slightly more complicated ones, yet still fairly the same. First is the product rule. So the product rule is first things first. That's basically what it means. Just as in multiplication, we're dealing with addition, repetitive addition. But for the product rule, we're going to be involving the multiplication of two functions. So basically it's like f of x times g of x. That is when we use the product rule. And the derivative of this is equal to the derivative of the first function, which for this one I'll name it a times b, okay? The derivative of a prime is the prime basically shows derivative, okay? That's important also for you to note. When you see, for example, y prime, it's referring to the derivative of y. And if you see x prime, the derivative of x. Similar. Basically, prime means derivative. So the derivative of a times b plus plus a times the derivative of b. So first things first and second things second. And the complicated thing here is to remember the order at which they go. But always remember that they're basically just going to be one by one. So if you notice, the prime is just moving to the right, one letter at a time. Actually, if you had three functions here like f, g, and h, all you'd be doing is a prime first, and then here a prime times bc, and then a times b prime times c, and a times b times c prime. So that's another expanded version of the product rule. Basically, just first things first and move the derivative across the letters. Now, an example of this is, for example, 3x plus 4 times x, and we're gonna get the derivative of this. So what you want to do here is we're gonna get the derivative first of the first function, which is 3 times b, which is x, and we're gonna add that to 3x plus 4 times the derivative of the other function, which is. And now from here, once we have laid out our equation, we're just going to simplify. So 3x plus 4 is 6x plus 4, and that is our derivative. Now the product rule is also very similar to the quotient rule. So the quotient rule basically is just the same thing, except our a and our b are referring to the numerator and denominator respectively, and the operation is now subtraction. So allow me to show you. Quotient rule. So for the quotient rule, as opposed to multiplication, obviously we're dividing functions. So the instance when this is used is going to be, let me use this is a new color. Anyway, f of x over g of x. This is when it happens. And the derivative of this is given as the derivative, okay, again we'll use this as a and we'll use this as b. The derivative of a times b minus a times the derivative of b. And this is all over b squared. And what some people do to remember is they assign this as low and this is high. So basically it would be written as low d high, high d low in some books, and they use that as their reference. However, for this one, I'm just going to use the technical version on how to remember it, because really it's up to you how you want to memorize that. So it's pretty much just the, again, first things first, upper before lower and then upper times the lower. Basically the first things first is referring to which one gets the derivative first. So let's try an application of the quotient rule. Consider, for example, x squared divided by 3x plus 2. So the derivative of this would be x squared's derivative first, so 2x times b, which is 3x plus 2, minus x squared times the derivative of b, which is 3, all over 3x plus 2 squared. Now, for the quotient rule, you don't really have to simplify. It's widely accepted that 3x plus 2 is already in simplest form, unless of course your final answer can still be cancelled and whatnot. But ideally, in most situations, this is acceptable. So it would most likely be up to your teacher. Anyway, so simplifying the left side, it will be 6x squared plus 4x minus 3x squared. And seeing as these two can be combined since they're like terms, we'll be basically getting 3x squared plus 4x over 3x plus 2 squared. And that is our final answer for the derivative. So we're on to the final rule. The final rule is the chain rule. This rule is what most people say to be the hardest rule. However, realistically, the only thing that makes this rule difficult is that it invokes all of the other ones. So that being said, as long as you know how to use everything else, you should be fine using the chain rule. Now, what is the chain rule used for? The chain rule is used for composite functions. What are composite functions? So basically it's like when it's f circle g of x. And composition is hard to see in terms of this format. Like in questions that they give you, you can't really see this version immediately. So essentially what you need to look out for are functions within a function. And this looks like this. So for example, we have x plus blank. Let's say that this is a constant squared. This requires the chain rule. The first function here would be the actual umbrella function, which is the one that's squared, and then the other function is the one inside, which is the minor one. I like to call it the minor function because it's not really the one that's being focused on here. So how do we use the chain rule? Basically, what you're gonna do is you're gonna derive the umbrella term first. So derive the umbrella and then multiply this by the derivative of the minor term. And sometimes the minor term also has another minor term. So that's why the chain rule is kind of difficult the most, because it really continues, and as the name suggests, it's a chain of derivatives. So let's try an example of this. What we can use here is x cubed plus 4 squared. Okay, so first thing that we're gonna do is we're gonna derive the umbrella term. we'll use the power rule. So we'll treat this all as one function, and we'll get 2 times x cubed plus 4 to the power of 2 minus 1, which is just 1. We're gonna multiply it by the derivative of the inside function, which is 3x squared. We can simplify this. We can get 6x squared times x cubed plus 4, which we can further simplify to 6x to the 5th plus 4 plus 24 rather, x squared. And that is our final derivative using the chain rule. Now, these rules are how to calculate, or how, not really how to calculate, but how to derive the formulas for the slope given a function. Now, all of these are variables that are given. So, what's it called? X is not a trigonometric or transcendental function like sine, cosine, or an exponential function. And those functions actually have different rules themselves. So that is what we're going to be tackling now. Okay, because those functions, they use all of these rules. But in particularly, transcendental functions concern themselves with the chain rule. So here is a list of easy conversions, or just something that's screenshotable for you guys so that you can remember the derivative formulas for transcendental functions. So trig functions here, trig functions. So first we'll start with sine x. The derivative of sine x is equal to cosine x. They're backwards. If this is y, this is x. So that might be a giveaway for you guys. Now the derivative of cosine x is negative sine x. Keep in mind that c brought a negative. You'll see more of that in a bit. Now, moving on. Tangent x. Tangent x's derivative is secant squared x. Not to be confused with secant x squared. This is a completely different thing. Now, next, we have the inverse trig functions. No, not inverse, sorry. The reciprocal functions, which is secant. Or rather, let's start with cosecant here. Cosecant x. This is equal to negative cosecant x and cotangent x. If you notice again, the c brought a negative. And the next one is secant x is equal to secant x tangent x. And lastly, cotangent, I'm getting OCD. Cotangent x is equal to negative cosecant squared x. So my suggestion in remembering this is to find the relations between the instances of the negatives and also the reciprocal functions of the functions involved. So for example, tangent x's derivative is secant squared x. And if you notice, cotangent, which is the inverse of tangent, has its derivative as negative cosecant squared x, which is coincidentally also the reciprocal function of sine, which is the opposite of secant, if that makes sense. Basically, they're connected. Cosine to sine, they're connected. Tangent to cotangent, they're connected. And cosecant to secant, they're connected. So it's a lot easier to memorize once you have them in comparison. Now, these functions are all following the chain rule. What does that mean? Or how does that look like? Basically, we won't always have sine x. Sometimes we'll end up having sine 4x or something like that. Now, the important thing to understand about trig functions is that the word sine itself, this is already a function. So, when we add an x here, we're effectively using the chain rule because we have a function encapsulating another function. So our umbrella here is the sine, and our minor term is the x. So if we're going to derive this, we'd have to get first the derivative of sine x, which is cosine x, times the derivative of x here in the middle, which is 1. That's why we get to here. Now, in a question, for example, with sine 4x, it would look like this. So again, we derive first sine 4x, which is cosine 4x, times the derivative of 4x itself, which is 4. And now this gets us to 4 cosine 4x. And that is basically how you apply the chain rule to all trigonometric functions. Now, how about exponential, logarithmic, and exponential, logarithmic, and natural log derivatives? So they have their own formula. So hold on, allow me to write them. Okay, so beginning with exponential functions. Hold on, let's remove this. Exponential functions are what pen should we use? Let's use this one. Exponential functions. So we're following the basic formula, which is d dx of, let's say, a to the power of x is equal to a to the power of x times ln a. So basically, we're just rewriting the term and then we're multiplying it to the natural log of the base. The base, again, here is going to be a. And now, let's say that x has a value, let's say that it's 4 or something. Basically, we're also multiplying this to the derivative of the upper function, which is x d over dx. It just so happens that in this example here, the derivative of x is 1. So it's the exact same. Now, there's a special case here. The derivative of e to the power of x. Now, let's analyze. So we're gonna write e to the power of x here again, and we're gonna type ln e. Now, convert this back into exponential form. Ln refers to e. Now, e should be the result. So e to the power of something should be e. And the only way for this to be satisfied is for x to be 1. So this, in effect, is going to be e to the power of x times 1, which thus means that the derivative of e to the x is just e to the x. That is how you prove that, and there you go. So that's going to be pretty useful throughout the rest of the topics. So now, what do we do about logarithmic derivatives? So logarithmic derivatives are they also follow a similar format. So also, by the way, this one we also must apply the chain rule here in terms of the minor function, which is just x. So now, the derivatives of logarithmic functions are given by this formula here. So let's label it with logarithmic functions. So our logarithmic functions are given by the derivative of log a, log b to the base a is equal to 1 over the natural log times the base, which is a, times b. And this is also equal, this also has to activate the chain rule, which is times the derivative of b. So there. If you want, I'll make this x so that it's less confusing. So there, x. Okay, and the other derivative that we need to worry about in terms of logarithmic functions is the derivative of the natural log, which is just an easier version of this, which is ln x, the derivative of ln x is equal to 1 over x times, of course, the derivative of whatever the x in the function is. So to try from both of these worlds, let's try deriving, for example, 4 to the power of 5x. So using this format, we're going to be getting the derivative of this, which is equal to 4 to the power of 5x times ln 4 times the derivative of 5x, which is 5. So this now is the derivative of 4 to the power of 5x. Now let's try a logarithmic function, which is, let's see, let's try the log of log 4 to the base, or no, log 4x to the base 3, and we're gonna derive that d over dx. So we're just going to follow the formula, which is 1 over 4x times ln 3, ln 3 times the derivative of the x function here, which is times 4, and these two will cancel out, so we will be left with 1 over x ln 3. That is the derivative of log 4x to the base 3. Alright, so there we have essentially all of the rules nailed down now, and we're back to the concept of derivatives. We're running it back now. Where are these concepts applied? Now, all of these concepts are applied to a bunch of different fields. This is essentially our wrap up for this supercut for derivatives. These rules and these setups for finding out the rate of change and etc., these actually allow us to apply the rates of change in a way that will benefit ourselves in the world. So for example, businesses who monitor the stock market and such, they monitor trends using economics, which uses derivatives as well. They use calculus. For physics, they use derivatives to get from displacement to velocity to acceleration. All of those are connected by calculus, and all of these tie into the real world. For the first time, maybe you might be thinking, wow, this is math that actually has application. And well, it's true, because calculus really is the study of how things change around you. Everywhere you go involves calculus, we just really don't think about it. So hopefully, after this video, I know it's a lot, and it's 47 minutes I think right now, but I hope you guys learned a lot, because these are really just the basics of differential calculus. And for the next video, I'm just going to be talking about implicit differentiation and how we're going to use it in terms of real life application, which is related rates. And yeah, so from there, we're going to move on to integral calculus, which I hope I can cover in a way that you guys can understand. But yeah, for now, that's it. Thank you everyone for watching this minute concept on calculus again, this time about differential calculus, and I hope that you guys picked up something from this video. So thank you everyone, and I hope you guys have a great day ahead. Thank you everyone, and goodbye.